In this video, we will discuss the Gram-Schmidt orthogonalization process. It's a very important topic in a digital communication system, and this method is actually used to find the orthonormal basis function. So, in order to get an idea about what is an orthonormal basis function, we will just brief the signal space representation of a signal. Okay, so from the idea of signal space representation of signal, we can say that m energy signals, for example, Si of t, or I can say that S1 of t, S2 of t, etc. up to Sm of t. So there are m set of signals, and these m set of signals can be represented as a linear combination of some other signals. Okay, for example, phi 1 of t, phi 2 of t, etc. up to phi n of t. And this signal is known as the orthogonal basis function, or very specifically, we can call it as orthonormal basis function. Okay, so that's the idea behind this signal space representation of a signal. Okay, any set of m signals, uh, very specifically energy signal, can be represented as a linear combination of n orthogonal basis function. So mathematically, you can write, for example, Si of t. In general, Si of t can be written as sigma j is equal to 1 to n, where n is the total number of orthonormal basis function, and this orthonormal basis function is represented as phi j of t. And this Sij is actually the coefficient of this orthonormal basis function, and the value of I varies from 1 to m because there are m signals. For example, if you want to represent a signal S1 of t, or you can write S1 of t as a linear combination of, for example, phi 1 of t, assume that there are three basis functions, okay, or the value of n is equal to 3, then you can represent S1 of t as phi 1 of t into S1 to phi 2 of t, then S13 phi 3 of t. So we can see that the signal S1 of t we can represent as a linear combination of phi 1 of t, phi 2 of t, and phi 3 of t. So the question is that how we can find a phi 1 of t, okay, and how phi 2 of t, and how phi 3 of t in this particular example. So Gram-Schmidt orthogonalization process is actually a method to find this phi 1, phi 2, phi 3. See, we already mentioned that any set of m energy signal we can represent as a sum of a linear combination of some orthonormal basis function. So Gram-Schmidt method is actually helps to find this orthonormal basis functions for a particular set of signals. Okay, so now we will explain this Gram-Schmidt orthogonalization process with the help of an example. So we'll discuss some equations, and we will try to explain the procedure with the help of example. So here in this particular question, it is given that using Gram-Schmidt orthogonalization procedure, find a set of orthonormal basis function to represent the three signals S1 of t, S2 of t, and S3 of t, as shown in figure. So in the question, it is given three signals S1 of t, S2 of t, and S3 of t. So we can see that S1 of t is signal which exists from 0 to 1, and the amplitude is 2. And S2 of t is a signal which exists from 0 to 2, and whose amplitude is -4. And S3 of t is a signal whose amplitude is 2, and it exists from 0 to 3. And we need to represent these signals S1, S2, and S3 in terms of some as a combination of some basis function or orthonormal basis function. So now we can see how we can approach this particular problem. So for that we can use this Gram-Schmidt orthogonalization procedure, and also we need to express each of these signal in terms of set of basis function. Okay, so first we need to find the orthonormal basis function, then we need to express each of these signal in terms of its orthonormal basis function. So we can first discuss the basic equation that we require to find this orthonormal basis function. So in general, this phi I of t, okay, that's an orthonormal basis function. Orthonormal basis functions are represented as phi 1 of t, phi 2 of t, etc. So assume that there are n orthonormal basis function. And in the question, it is given that three sets of signals. So S1, S2, S3. So value of m is equal to 3. Then the orthonormal function phi 1 of t, phi 2 of t, etc. So there will be n number of orthonormal function which should satisfy this condition that n should be less than or equal to n. Okay. So maximum you will get 3 or less than that. So each orthonormal function we can calculate by using this particular formula, that is phi 1 of t can be written as g1 of t by root of 0 to t g1 of t the whole square dt. Okay, this particular expression, that is 0 to t g1 of t, is another signal. This is known as the orthogonal signal, and we need to make it orthonormal. So for that we will divide this orthogonal signal by using its energy. So this term is actually indicating the energy of that particular signal. Okay, so we will find the orthogonal signal and we will divide it with a norm of that particular signal. Okay, here we can say that is energy. So this equation, root of 0 to t g I of t whole square dt. So the term g I of t whole square dt is actually indicating the energy of the signal, and you will take the root of energy. So that is actually this particular equation. So then we will get orthonormal basis function. Orthonormal basis function. So this is a general formula, and if there are n orthonormal function, you need to substitute I is equal to 1 to n. Okay, so we can write g1 of t by and g2 of t, g3 of t, etc. And next question, how we can find g1 of t, or in general gi of t, how we can calculate. So gi of t is actually calculated by using the second formula, that is gi of t is given by si of t. Si of t is a given signal. For example, if you want to calculate g2 of t, so we can use s2 of t minus, for example, in this particular case, okay, this I value is 2, so 2 minus 1. So we can write j is 1 to 2 minus 1 is ij by j of t. Means in order to calculate g2 of t, we need to substitute s2 of t minus here only one value. So we can write very specifically here it is 2, because I value is 2, and j value we can put 1 here because j is varying from 1 to 1, so only one value, and phi 1 of t. So this is a formula to calculate g2. Okay. Then again there is a term, if similarly you can calculate g3, g4, etc., and you can substitute in the first equation. So again there is an unknown quantity, that is what, the coefficient Sij. So now we need to evaluate Sij. So the coefficient Sij we can calculate by using the third formula, that is Sij is equal to integral 0 to t Si of t into Sj of t dt. That is, if you want to calculate S to 1, you can use the formula 0 to t S2 of t and phi 1 of t dt. Okay. So another important point, if you want to calculate phi 2, okay. So if you want to calculate phi 2 of t, we need g2. So if you want to calculate g2, you require phi 1. Okay, that's a idea behind orthonormal function. So it's a series of operations. So first we need to find out phi 1, then only you can find out phi 2. If you find out phi 2, you can find out phi 3, etc. And using this formula, you can calculate the coefficient. So this is the third formula that we required to evaluate this particular question. But there's a special case occurs when phi 1. Okay, when you want to evaluate phi 1 as a special case instead of this g1 of t and etc., because there is no expansion for this particular formula when I value is equal to 1. So when I is equal to 1, it's a very simple formula. You can take the first signal S1 of t, okay, S1 of t as the reference, and you can divide with its root of its energy. So E1 is actually the energy of the signal S1 of t whole square dt. Okay, so we will start from this particular point. Actually, we required a single formula phi I of t. There is an unknown quantity gi of t. Gi of t you can calculate using the second formula. And the second formula, there is another unknown quantity, that is Sij. That Sij you can calculate using the third formula. And finally, we required one more formula because we cannot evaluate phi 1 by using this. So for that, when I is equal to 1, you need to use a simple formula, that is simply S1 of t by root t, because we don't want to use G1. So we will assume that G1 is simply S1. Okay. So that's a basic formula we required to evaluate the Gram-Schmidt orthogonalization procedure, or we can apply this formula. So we can discuss about the solution part. Okay, in the question, it is given 3 different signals S1, S2, S3. So we can start from phi 1. So we need to evaluate phi 1 of t. So we already discussed that the formula to calculate phi 1 of t is simply S1 of t by root E1. So S1 of t is given in the question, that S1 of t is a signal which exists from 0 to 1 and the amplitude is 2. So this is a signal S1 of t and the amplitude is 2. Okay. Now we need to find phi 1 of t. So in order to evaluate phi 1 of t, we need to find E1. So E1 is actually the energy of the signal S1 of t. So 0 to t S1 of t, the whole square dt give you E1. So we can see that signal exists from 0 to 1. So integration becomes 0 to 1. And here it is 2. So you can put 4, 2 square becomes 4. And answer will be 4. Okay. So you'll get energy is equal to 4. So phi 1 of t, you can write 1 by root 4, that is 2 S1 of t. So we got the first orthonormal basis function, that is phi 1 of t. So we can plot that phi 1 of t is equal to S1 of t by 2. Okay, this is 1 by 2 S1 of t. So we can divide the amplitude, or you can multiply the amplitude with 1 by 2. So here it is 2. If you multiply with 1 by 2, it becomes 1. So you will get your first orthonormal function, that is 0 to 1, and the amplitude is 1. So this is phi 1 of t. Okay. So very simple process. Take any one signal as S1 of t. Okay, or take the first signal itself, and you can evaluate using this particular formula. And there is a term E1, that is actually energy. Energy you can evaluate by using the integral formula, and you can draw the waveform. So we got phi 1 of t. Okay. Next step, we can represent S1 of t in terms of phi 1 of t. So that's the next step. So here you can see that we got a relation that phi 1 of t is equal to S1 of t by root t. So from this particular equation, you can write S1 of t. If you cross multiply this, you will get root of E1 into phi 1 of t. So actually this term represent the first coefficient S11, because when you write S1 of t, it will be S11 phi 1 of t plus S12 phi 2 of t plus S13 phi 3 of t plus etc. So we don't know how many orthonormal function. Anyway, maximum there will be 3 terms. Anyway, we need to evaluate. So in this particular case, first case, we got a relation between phi 1 of t and S1 of t. There is no term of S12 and S13 or etc. So we can assume that there is only one non-zero coefficient, that is S1. So in place of S11, it is from the previous example, it is if you write this particular equation, you can write S1 of t is equal to 2 into phi 1 of t. So we can say that this term S1 of t is equal to 2 into phi 1 of t. So your coefficient S11 is equal to 2. Okay. So, and other coefficients will be 0. Okay. Now we will discuss the second part, that is we need to evaluate phi 2. So in order to evaluate phi 2, we can use the general formula. Here phi I of t is gi of t by root of 0 to t gi of t the whole square dt. So in this formula, if you put I is equal to 2, you will get phi of suffix 2 t. In place of I, you can put 2. So g2 of t by energy of that signal. Okay. And how we can calculate, then we need to evaluate g2. So general formula for gi of t is given here. So this is the general formula for gi of t. And in this particular formula, you can put I is equal to 2. So if you write I is equal to 2, it becomes G2 of t into S2 of t minus sigma j is equal to 1, 2. Here I value is 2, so 2 minus 1, S2 of j, phi j of t. 2 minus 1 is 1, so you need to write only one term, that is S21. Okay. So this is the expression for G2. So in order to evaluate this particular equation, we required actually S21. Okay. S21 and phi 1 of t. And we'll see what's the formula to evaluate S21, because there is a general formula for Sij, and in this particular formula, you can substitute the terms, that is we required S21 means I is equal to 2 and j is equal to 1. So if you evaluate, you will get S21 is equal to integral 0 to t, S2 of t, phi 1 of t dt. So we can find S21. Okay. So in order to evaluate S21, so in order to calculate S2 of S21, actually we required S2 of t. So we can plot S2 of t here, which is a signal access from 3, and this is -1, -2, -3, and -4. So it's a signal 1, 2, 3, 4. So signal access from 1 to 2, sorry, 0 to 2, it's -1. That's S2 of t. And we need to multiply with phi 1 of t. So already we got phi 1 of t. Phi 1 of t as a signal which exists from 0 to 1, and the amplitude is 1. So I can plot that also. So I need phi 1 of t, that is 0 to 1. The amplitude is 1. And in order to calculate S21, we need to multiply these two signals. So if you observe this particular signal, we can say that the signal exists S21 is from exists from 0 to 1 actually. From 1 to 2, here it is amplitude is -1, but here it is 0. So the first signal amplitude is -1 and second one amplitude is 1. So 1 t. So we'll get -4 as S21. Okay. So now we got S21. Now we can substitute in this particular equation S21. So S21 is -4. So we can substitute here, that is S2 of t, and G2 of t you can calculate by simply multiplying this phi 1 of t with -4. So this is a signal S2 of t. S2 of t is a signal which exists from 1 to 0 to 2, and the amplitude is -4. This is S2 of t. And the second signal, actually phi 1 of t into S2 of 1. Phi 1 of t is, you can see that this is amplitude is 1 and we need to multiply with minus 4. So it becomes minus 4 here. So minus 4, uh, minus 1, minus 2, minus 3, minus 4 from 0 to 1. Okay. So that's a signal actually minus 4 into phi 1 of t. So the second term. The second term I can write minus 4 into phi 1 of t. And what's the next operation is that you need to subtract the second signal from the first signal. So graphically, if you look at this particular signal, you can see that if you subtract these two signal, you will get a new signal which exists from 1 to 2 and whose amplitude is minus 1. So we'll get a signal which exists from 1 to 2 and the amplitude of this particular signal is minus 1. That is minus, or we can say that is G2 of t. The signal G2 of t. G2 of t is S2 of t minus the second signal. Okay. And now we got G2 of t. So we can substitute this G2 of t in phi 2 of t. So in order to calculate phi 2 of t, you need to divide its energy, root of its energy. So if we calculate the energy of G2 of t, okay, we can calculate 0 to 2 G2 of t the whole square dt. We know that it exists from only from 1 to 2. So 1 to 2, the amplitude is minus 4. So minus 4 the whole square dt. So you'll get 16. So now we got 16 here. And if you substitute in this particular formula, it becomes G2 of t, right here, G2 of t by root 16. So we'll get 1 by 4 G2 of t. Now we got phi 2 of t. So we can plot here. G2 of t is already, we know that is G2 of t is a signal which is exists from 1 to 2 and the amplitude is minus 1. Okay. So that's a signal G2 of t. Now we need to multiply this signal with 1 by 4. Then you will get phi 2 of t. So we can plot phi 2 of t. Again, it exists from 1 to 2. And if you multiply with 1 by 4, the amplitude becomes minus 1. So this is your new signal, which exists from 1 to 2, and the amplitude is minus 1. That is phi 2 of t. So we got two signals, phi 1 of t and phi 2 of t. Now we need to express the signal in terms of phi 2 of t, or we need to express S2 of t in terms of this phi 2 of t. In the previous expression, we know that G2 of t is S2 of t minus S21 phi 1 of t. So, and we also know that G2 of t, G2 of t, or okay, we'll write another way. That is here you can see that phi 2 of t is equal to G2 of t by root of its energy. So we can write 1 by 4 G2 of t. So you can write G2 of t as 4 into phi 2 of t. Okay. So if you rearrange this particular equation, S2 of t, you can write minus S21 of phi 1 of t, and if you move this to left side, it becomes plus. Then G2 of t, you can write plus 4 phi 2 of t. And we know that S21 is minus 4. So minus 4 phi 1 of t plus 4 phi 2 of t. So we can see that S2 of t can be represented as a linear combination of phi 1 of t and phi 2 of t. So phi 2 of t is other second orthonormal basis function. So in similar way, we can find the next signal, that is phi 3 of t. So now we need to discuss how to find out phi 3 of t. So third basis function. So the general formula is phi a of t. So we can write phi 3 of t can be written as g3 of t divided by root of energy of this particular signal, that is g3 of t the whole square dt. Okay. Our next problem, what is g3 of t? So g3 of t you can calculate by using this particular equation. So g3 of t is given by s3 of t. So here I is equal to 3. So you can substitute I is equal to 3 in this particular equation. So you'll get s3 of t, and j is equal to 1 to 3 minus 1, that is 2 s3j phi j of t. So if you expand this, you will get s3 of t minus s3 1 phi 1 of t minus s3 2, because j value is varying from 1 to 2. First case j is 1 and second case j is equal to phi 2 of t. So we got an equation for G3, but there is some unknown quantity, that is S31 and S21. So we need to calculate each quantity. So first we can write S31. S31 is equal to, by using this particular formula, it is 0 to t uh, S3 of t into phi 1 of t. This is one equation for S31 coefficient, and for S32 it becomes 0 to t S3 of t into phi 2 of t. So now we need to evaluate these two coefficients. So in order to calculate S31, we required S3 of t. So S3 of t is a signal which exists from 0 to 3. Okay, we can plot it's from 0, 1, 2, 3, and 2. So the amplitude is 2, that is actually S3 of t, the given question. So now we need phi 1 of t. So phi 1 of t, we already evaluated phi 1 of t. So phi 1 of t, it's 1 from 0 to 1. So this is phi 1 of t. Now we can see that we can evaluate S31 by using this formula. So we need to multiply S3 of t and phi 1 of t. So it becomes 0 to 1, and first signal amplitude is 2 and second signal amplitude is 1 t2. So you'll get 2. Okay, and remaining values it is 0. Okay, and now we need to evaluate S32. S32 we can evaluate S3 of t into phi 2 of t. So we required what you call phi 2 of t. So phi 2 of t is actually existing from 1 to 2, and its amplitude is minus 1. So this is actually phi 2 of t. Now we can see that we need to multiply this S3 of t and phi 2 of t. So we can say that the non-zero magnitude S3 only exists from 1 to 2, because phi to 2 exists only from 1 to 2, and otherwise it's 0. So for that duration it is 2, here it is minus 1. So we'll get it's minus 2. So you got these two quantities, you can substitute here. So it becomes S3 of t minus S31 is actually 2, and phi 1 of t minus S32, it's minus 2. So minus 2 phi 2 of t. So this is the equation for G3 of t. So now we need to calculate G3 of t. So we require S3 of t. So we know that S3 of t is a signal which exists from 1 to 3, and the amplitude is 2. So this is S3 of t. Now we need to subtract 2 phi 1 of t. So we can plot 2 phi 1 of t here. So phi 1 of t is 0 to 1, the amplitude is 1, and we need to multiply with the constant 2. So it becomes 2 from 0 to 1. So this is actually the signal 2 phi 1 of t. Okay. Now we can consider the third signal, that is minus 2 phi 2 of t. So phi 2 of t is actually -1 from 1 to 2, and if you multiply with -2, it becomes positive. So you can see third signal, that is from 1 to 2, its amplitude becomes 2, because we are multiplying the signal phi 2 of t with -2. So phi 2 of t is actually -1 amplitude, and if you multiply with -2, it becomes 2. Now we need to evaluate this. So if you observe this particular question in graphical way, we need to subtract 2 phi 1 of t and -2 phi 2 of t from the first signal S3 of t. So we can see that from 0 to 1, first signal amplitude is 2, second signal amplitude is 2. So 2 minus 2, 0. So you will get 0 in this duration. Okay. So this is actually G3 of t. For this duration, the amplitude is 0. And from 1 to 2, the first signal amplitude is 2, second is 0, and third one is 2. So 2 minus 2, again 0 you will get. Okay. And for the third part, 2 to 3, the remaining amplitude is 2 to 3, will be 2. So you will get G3 of t as 2 from 2 to 3. Okay, we got G3 of t. Now we can go back to the first equation. So here we got G3 of t. Now need the energy of G3 of t. So we can calculate it from 0 to t, G3 of t the whole square dt. So G3 of t exists from 2 to 3, and the amplitude is 2. So 2 square dt. So we'll get 4 here. Now if you substitute in this particular equation, phi 3 of t is 1 by root 4 G3 of t, which is 1 by 2 G3 of t. So if you multiply the amplitude of G3 of t with 1 by 2, it becomes 1. So you will get your phi 3 of t like this. Phi 3 of t becomes 0, 1, 2, 3, 2 to 3. The amplitude of the signal is 1, because we are multiplying the G3 of t with 1 by 2. So amplitude is 1. So now we got the three signals, phi 1, phi 2, and phi 3. Now we can express this phi 3 of t in terms of, S3 of t in terms of its orthonormal basis function. So last step, we can express S3 of t using its basis function. So we already know that G3 of t. So from this particular relation, G3 of t can be written as S3 of t minus S3 1 phi 1 of t minus S3 of 2 is phi 2 of t. And we know the coefficients values. We can substitute here. S31 is 2 and S32 is minus 2. So, and we know one more thing, that is phi 3 of t is G3 of t by 2. Okay. Now we can substitute all these quantities here, and we can write S3 of t is equal to 2 phi 1 of t minus 2 phi 2 of t plus 2 phi 3 of t. So we got an expression for phi 3 of t. So now we can conclude that the first signal S1 of t we can express. So we already got it is 2 phi 1 of t. So definitely the other two terms will be 0, 0 phi 2 of t plus 0 phi 3 of t. Okay, from the first analysis. And S2 of t you can write it's, I think, minus 4 phi 1 of t plus 4 phi 2 of t, and the third is 0. Okay. The third signal S3 of t can be represented as 2 phi 1 of t minus 2 phi 2 of t plus 2 phi 3 of t. So we can express all these signals in terms of its orthonormal basis function. So here three signals. So m is 3. So we don't want to evaluate n greater than that. Okay. So maximum you need to evaluate up to n is equal to 3, because n value is less than or equal to n. In some cases, you can go less than that. In that particular case, you will get the coefficient value 0 when you evaluate. Okay, then we can start. So one more concept we can say that if you write this particular equation from this, you can express the vector notation of the signal. Sometimes I'm asked to find the vector notation. So the coefficients you can directly write 2, 0, 0 is a vector notation of signal S1. S2 similarly you can represent -4, 4 and 0. Okay, and S3 you can write 2, -2. So this is actually the representation of signal S1 of t, S2 of t, S3 of t in terms of its orthonormal basis function, phi1 of t, phi2 of t, phi3 of t. So finally, you can plot all these signals, phi1 of t. So phi1 of t is a signal which exists from 0 to 1 and the amplitude is 1. And second signal is, second orthonormal function is phi2 of t, which exists from 1 to 2 and the amplitude is -1. And the third signal is phi3 of t, which exists from 2 to 3 and the amplitude is 1. Okay, these are the three basis functions. By using these three basis functions, we can represent the three set of energy signals S1, S2, S3. Okay.